Thanks for coming, everyone. Today we'll talk about correlating application and database performance using OTel, aka SQL commenter in action. Quick intro. My name is Lin. I head the APM instrumentation team at SolarWinds, and here's my colleague.
Yeah, hi everyone. I'm Tammy Baylis. I'm a developer on Lin's team, and I'm also a part-time OTel contributor. Back to you.
Okay, so I'll start with what was the problem we wanted to solve. SolarWinds has an application and database monitoring components in our product, and we wanted to integrate them to help customers answer questions like, is my application request taking long because of the state of the database? Or conversely, from the database point of view, where are these expensive queries coming from? Our APM is built on top of OTel, which is great because OTel comes out with like lots of instrumentation out of the box for different database server types or database types and a rich set of data. But the data gathered is really from the client perspective. So compared with the typical distributed tracing for HTTP, where you have service A making an HTTP request to service B, and you can see that in the distributed trace, thanks to the trace context that's propagated via the HTTP header. You see in this example, when service B makes a database call, all of that insight is really from the client side only, and the database client span really kind of links to nothing. Wouldn't it be nice if it actually could link to something? So a little bit about context propagation. As we saw before, for HTTP, it's pretty well defined in the W3C trace context spec. It's propagated via the trace parent and trace state headers. For messaging systems, most systems support the metadata header or property concept, and we see a lot of OTel SDK implementing them this way, even though there's no explicit spec. For databases, it's a lot murkier. There is a discussion happening right now in the PR that's highlighted, which actually gives a lot of insight on how observability vendors tend to do this. And there are a lot of different approaches, and it could actually be very server-specific, depending on what the server supports. In terms of native server-side instrumentation by the database vendor, there are not as many examples in the wild, but MySQL Enterprise Edition does do native server-side tracing using the MySQL query attributes mechanism. And Vitesse, which is a CNCF database project, uses SQL comment, which leads to our next topic by Tammy. Use the clicker if you want.
Oh, yeah. Thanks, Lin. Enter SQL commenter. SQL commenter is an observability technique, and essentially it's when database clients inject structured comments into queries following standard SQL syntax. So in this very simple query, select one, it's been appended with a SQL comment, flanked by the slashes and asterisks. And this SQL comment has two key value pairs. The first is a shortened version of a trace parent, the full thing with version, trace ID, span ID, and trace flags. And this other KV is some database driver metadata for what performed the database query. And in this case, it's the MySQL connector, version 8.4.0. SQL commenter was originally developed at Google, and it's still at the original Google SQL commenter repo right there. It's been partially migrated to CNCF to this OTel repo. A bit more on that later. SQL commenter right now has experimental incorporation into OTel for trace context propagation. So it's the instrumentation of database driver libraries or object relational mappers, aka ORMs or ORMs, that do the injection of the comment. And right now, configuration is programmatic and opt-in. In this Python example, we have the init of a SQL Alchemy instrumenter, very popular ORM called SQL Alchemy. And in the call to instrument, we are saying, OK, enable commenter true, which will add the whole SQL comment. If we pass these commenter options, OTel values true, that'll include the trace parent. DB driver false would not include the database driver KV. Big table, but I'll go quickly. This summarizes the current state of the implementation of sqlcommenter for OTel right now. For Golang, there is a separate OTel SQL library that was developed by Sam Xie, or XSAM, and it will provide SQL commenting or any database interfaced by the database SQL library. For Python and Node.js in OTel, there are multiple instrumenters that support SQL commenting. For example, for the MySQL drivers, MySQL Client, MySQL Connector, MySQL2, or Postgres like PsychoPG2, or the ORM SQL Alchemy I mentioned. They're all there in the public repos. For Java, Ruby, Python, Java, Ruby, PHP, it's a bit more complicated right now. For Java, there's a PR out by Lori T right now to add SQL commenter to JDBC and R2DBC. I always have trouble with that one, which would enable commenting at the driver level for MySQL, etc. But there are SQL commenters for Spring and Hibernate that are still really in the Google repo and not in language-specific OTel repos. Similarly, for Ruby and PHP, there's Marginalia and Laravel SQL commenting, respectively, in the Google repo still. Not actively maintained, hasn't been released in a few years, and for all other languages like .NET, nothing in OTel nor Google. What does all that give us? These implementations let us bridge that gap between the client application and the actual server query. So this is the same diagram that Lin showed before, but this time we don't end with like a question mark. The same trace ID generated for the root span at service A goes by HTTP context propagation to service B, and service B uses the same trace ID in the SQL comment that is included in the statement for the database server. Let's look at what a comment actually looks like. Lots of text, sorry, but we have some arrows. In the top is an example of an OTel collector debug span, and that comes from the instrumentation of the MySQL framework in Python. And we see here it has a trace ID and a span ID. Y'all have probably seen something like this before with an OTel collector. In the smaller box below here, this is an entry in a MySQL general log of the requested database server. And very briefly, a general log in a SQL server is one or more log files that contains records of all queries and server operations. So it's a pretty detailed history if you enable it. So now visually we can correlate the span that was generated with the actual query. Labeled in red, the trace ID starting with CDC is the same in the span and the SQL comment, and so is the span ID labeled in blue. And one thing to consider is that SQL commenter as a feature is really just this simple insertion of the matching trace context and other metadata. It's one piece of the trace context correlation puzzle, and Lin's going to explain more about how we use it.
So like Tammy mentioned, SQL commenter puts that context in the query. How to use it? Well, conceptually, we could, like she showed, look at the server log, or we can interrogate some system views and sort of parse it out mentally and try to piece things together. That's obviously not great and tedious. What our product built on is the fact that our database monitoring also samples the queries seen on the server side, similar to how instrumentation will sample requests for detailed tracing. So when our database monitoring detects in the sampled query that there is the trace parent comment, it can parse that out, and then we start building a correlation mapping between the trace and the query sample. This is keyed on the query text and other metadata, such that we can say an APM query fingerprint was executed by a particular service on a particular database instance. Well, that was simple. Let's ship it. Not really. This is software, so we ran into a big limitation in the form of prepared statement. Prepared statement. So database servers have to parse and then plan and optimize a query when it's received. Prepared statement, which is supported by certain databases, optimized for the case of repeatedly executed queries. The way it works is kind of simplified in this diagram. The client will make a prepare call with the actual statement text to the server. Server parses it and stores it, and then hands back a statement ID. And then to actually execute that statement, the client will send just the statement ID and any parameters that need to be bound into the placeholders. So one major bonus of this is that it prevents SQL injection, because bound parameters are not treated as SQL. The big problem for SQL commenting for us is that there is no opportunity for the client instrumentation at the execute point to update the trace context. So it's always frozen as the same one that was passing in the prepare. OK, well, one way to solve this, let's just not insert the context for prepared statements. That was easy, and that's actually how we sort of go about this for certain languages. We just don't do the injection for prepared statements. But what we found with our APM Java custom distro, where we added support for SQL comment ourselves, is that by not inserting into prepared statement, it was making this integration pretty much useless, because Java ORMs like Hibernate use prepared statements heavily. So by not inserting, we don't have any integration. So we had to look a little harder. We looked a little harder and understood that a lot of client APIs offer abstraction to provide a uniform API even when the server does not support prepared statements. So kind of, again, simplified in this diagram, the API presented could be something like make a prepare call. And this is the API that's offered to higher level callers, like your actual application or your ORM. So this database client is generally like the driver or adapter level client. You make a prepare call, you bind some parameters, you execute it. Or it could be as simple as you just make an execute call with the placeholders. And if it's in actual prepare statement mode, it will actually go and do the prepare and execute. But if the client is in emulation mode, or if the database server does not support prepare statement, essentially, the client will actually construct the final statement and interpolate in all the parameters, and then send it as a non-prepare statement to the server, which in this emulation mode, it actually kind of bodes well for the ability to propagate the correct trace context. So, but wait, there's a tiny bit more. Client-side cache. Many drivers and adapters support statement caching to skip the processing work that's needed before actually making the execute call to the server. This pre-processing work could be templating the statement, or actually making a prepare call and getting back like the reference statement ID. So this diagram shows the simplified version again, that on getting that statement, the client will go and check the cache for a processed version. And only if it does not find it, then it will go through the work of processing the statement and putting it in a cache. If the cache key is the statement including the full comment, it means on the good news is that the correct trace context actually could be propagated, sometimes even for a server-side prepared statement. The bad news is by essentially making every statement unique, we are interfering with the caching, causing unnecessary processing and like really rendering the cache useless. And this would be both on the client side and the server side. We took some quick looks at how it is in the JDBC world, JDBC driver. So the MySQL connector J driver by default does emulation and does not have client-side cache enabled. So in this case, it actually kind of is probably worth doing. A different story with the Postgres database driver, where client-side caching is enabled and actual server-side prepare statement is also enabled, in which case this would cause quite a bit of performance overhead. Is this all worth it? Well, what I can say is that the type of end-to-end insight that's possible to build on top of this trace context propagation is pretty neat, and I'll show like a super quick record demo from our product. Here we have a trace that has like the database span, and oh, now it's doing the spinning. Well, it is a demo, even if it's pre-recorded. I don't know. I could skip the demo if it's just not going to run. Yeah. Well, yeah, I'll leave it to your imagination, but it's pretty nice. We can traverse from the span to the database query and database insight, and then traverse back. But yeah.
So sorry about that. We were going to show our amazing backend and what it's doing. But anyway, pretend that you saw our great demo, and we're going to share what could be next based on our own experiences using OTel for a backend and what we've seen in the community. So ideally, this is something that all the database vendors would implement, which is native support of trace context propagation. But it's a bunch of different vendors, and that would probably be slower than an OTel project, which isn't super fast either, but it could be possible. And there's a recent OTel SemConf PR that came out last month by user since June, and it proposes some database context propagation definitions in the SemConf. This was recently spun off their same .NET PR to add sqlcommenter, as well as those Java PRs I mentioned by Lori T earlier. And this would be great to define a vendor-agnostic context propagation mechanism for OTel so that everyone in the open source community can use it too, and not just people paying vendors. The downside, of course, is the high cardinality values like trace parent, and this is a link to that issue. Screenshot on the top right. If that gets adopted as an OTel project, it'd be great if there were more implementations that were resumed through more community PRs. So merge and release that JDBC PR, start new PRs to migrate Java's Hibernate and Spring, Ruby, and PHP's ORMs from Google over to OTel. This screenshot in the bottom right just shows the coverage that the original Google SQL commenter provides, and that code is still there and still valuable. Last thing I want to share is kind of specific to OTel Python, because I worked on it a bit, and my question is, how do we generalize instrumentation and context propagation for all the different database client permutations that are possible? Or who should be writing the SQL comment? For pretty much all Python applications that connect to a database, you have to use a database driver, and that's your MySQL connector, etc. I mentioned already. SQL Alchemy is helpful, but it's actually optional. Same thing for Tortoise ORM or Django's ORM, for example. So just to go back a bit, actually, there is some SQL commenter implementation for all of the above, but not all of them, and there are some inconsistencies I'm going to talk about next. Two black boxes again. This time, these are just both two MySQL log entries we're looking at with SQL comments. The first one should look familiar. It's a SQL comment with a trace parent and some database driver metadata, and that's what happens when you enable SQL commenting for Python's MySQL connector driver instrumenter. This second one's pretty interesting because we've enabled SQL commenting in the instrumenters for both Flask and MySQL connector. We still get a single SQL comment with a trace parent and driver information, but it's also been enhanced with some web app info like the controller request city is what it's called, or the route/city. And it's pretty neat. The Flask instrumenter for OTel gathers that web app info at time of tracing, and instead of writing a comment, it attaches it to the current OTel context, and the SQL connector instrumenter checks the existing context and enhances the comment and write. So that's pretty neat for those vendors and users looking for it. However, if you enable SQL commenter for the Django ORM instrumenter and MySQL connector, we get the problem of two comments. They both have trace parents with the same trace ID starting with BCA, labeled by the red arrows, but they have different span IDs. So this is a problem because backend developers don't necessarily know which comment to use if there's 0, 1, or more. This also contradicts the original Google spec for SQL commenter, which states that if a comment's already there, you shouldn't mutate the statement. Possible solutions moving forward: should it always be up to the user to decide which instrumenters are enabled or disabled, or which are doing SQL commenting? Should it still be the instrumenter's job, and should they all be like Flask, where they attach KVs to the current OTel context before the comment is only written by the database driver? Or should they check for a comment first and skip if it exists, something simple like that? Or maybe it should be the SDK that does it instead through a propagator. And so that's why PRs like the open one for the SemConv are really important. It'd be great to have some standardization across languages and database frameworks. To summarize what we talked about today, propagating context to database servers helps support end-to-end observability. One method is sqlcommenter, which is the injection of comments into query statements. And currently, there's open discussion about whether or not the OTel SemConv should define sqlcommenter as a standard. We note that several OTel language instrumenters already support this, but inconsistently, and we got to consider the performance impacts. Thank you.